today lecture we'll be discussing the topics phase trajectory of the second order system, limit cycle, and also we'll have the MATLAB simulation of the example. This is a very important lecture. We'll come up with the concept limit cycle. This is a very, very powerful term in nonlinear system synthesis. If you go back to our last lecture, based on the local liberation of the system and the eigenvalues whatever we had, and based on the eigenvalues, we can come up the conclusion circle. So we have the based on the eigenvalues, we have the different terms. One node, circle, saddle point, and focus. So different condition for the equilibrium point we had, right? So these are the concepts anyways we'll be having today lecture as well. But in extra things we'll be doing in today lecture is limit cycle. This is very, very important when this condition will arise. So let's start with the example. Let's consider the second order system. X double dot plus theta so squared minus 1 x dot plus x equal to 0. So this is the second order system. So to study the eigenvalues problem, we can convert into first order ODEs. So we can apply the change of variables. So for that, we can write x1 equal to x and x2 equal to x2 equal to x dot. And from this, we can write x1 dot equal to x2 and x2 dot equal to, we can write minus x1 plus epsilon 1 minus x1 square and x2, right? Let us define this equation as f1 x1 x2 and this equation f2 x1 x2. And to find the equilibrium point, we have to put f1 x1 x2 equal to 0, or you can write x2 equal to 0. And from the second equation, you can write f2 x1 x2 equal to 0. And from this, we can write minus x1 plus epsilon 1 minus x1 squared x2 equal to 0. And if we substitute x2 here 0, so we'll have x1 equal to 0, right? The equilibrium point for this particular problem means the equilibrium point have 0, 0. You can write xc, which is x1e, x2e, this is 0, 0, right? Now we'll find the Jacobian matrix. The Jacobian matrix we can form J equal to dou f1, dou x1, dou f1, dou x2, and dou f2, dou x1, dou f2, dou x2. Let us find the individual terms here. Dou f1, dou x1 is found to be, so if you take the derivative, if one function with respect to x1, it is 0, and dou f1, dou x2, which is 1, and dou f1, dou f2 to x1, we get minus 1, and we'll have minus 2x1 x2 into zeta, right? And dou f2, dou x2 will have zeta into have zeta 1 minus x1 square, right? Now we can substitute these terms here. This term we can substitute here. So we'll have, again, from 0, 1, minus 1, 2 x1, x2, zeta, and zeta into 1 minus x1 square, right? This is our Jacobian matrix at 0, 0 equilibrium point, say found to be 0, 1, and minus 1, and we have zeta, right? Now, if you want to find the eigenvalues, we have to find the characteristic equation of this J matrix. This is also sometimes called system matrix. You can define. So here we can write x1, x2 dot. This is also dot. We can write 0, 1, minus 1, and zeta into x1, x2, right? And this is equal to the linearized system. Linearized system. This process we have done multiple times in this course. And here, now we can find this is the A matrix, we can say. So from this, the eigenvalues you can find. The I minus A equal to 0, and the characteristic equation will have lambda minus 1, 1, and lambda minus zeta, right? And this is equal to 0. And the characteristic equation lambda minus zeta, and minus plus 1 equal to 0. And the roots or eigenvalues, we can find lambda 1, 2, we can write zeta plus minus zeta square minus 4, divided by 2, right? Here, if you notice carefully, for the different values of zeta, we have different eigenvalues, right? So let's look based on the range of zeta, the eigenvalues are classified as at zeta equal to 2. If you notice carefully, at zeta equal to 2, we are getting 2 eigenvalues which are basically 1. So this we can say eigenvalues are same and positive. So what does mean actually? This is very, very important here. In our last lecture, if you notice, we did not come up something like this, when the eigenvalues are equal, not distinct. And there's, of course, both are positive. So this is special in this problem. And this actually creates the limit cycle problem. So let's do the other values. I'll come to this point again. So let us again, if zeta is greater than 2, in this case, if you notice, lambda 1 and 2 distinct and positive, right? That is obviously, if we come up this condition in this expression, we'll have distinct and positive. That is clear. And let's have if zeta is less than 2. In this case, the eigenvalues will be complex conjugate with real part, we'll have positive real part, of course. Here, if complex like this, 2 complex with positive real. If theta equal to 0, in this case, eigenvalues are basically equal to 0, then it will be only will have complex conjugate eigenvalues, but real part will be 0. So in this case, lambda 1, 2 will be complex conjugate with the real part 0. Right. So this is very, very important conditions for this particular problem. Now, if you come up with the now different scenario, so here let's assume here we have different trajectory for this zeta value, which varies from minus lambda to, for example, minus infinity to plus infinity, for example. Sorry, let's assume minus alpha to plus alpha, the zeta varies. So in that case, we can have different scenario when the zeta varies from minus, or we can write when zeta is less than 0. In this case, if you notice here, if it is less than 0, so here we'll have, this is negative part, but this part will be complex conjugate. This part will be complex, right? So in that case, if you remember what you have done in the last lecture, so in that case, we'll have stable focus, right? So in that case, we have the plot something. We may have something like this. So it is converging to 0, right? This is what you have done in the last lecture. And if zeta is equal to 0 for this case, in this case, we can write. So these are the conditions we can assume the special cases, because since zeta if it is 2, then we can come up with easy conditions for the eigenvalues. And this is the actual what happens if it is varies from minus to plus. So now if zeta equal to 0 in this case, so what will happen? If it is 0, then only we'll have this part, right? It will be complex conjugate with real part 0. So in that case, what you have studied will have center, right, or vortex. So its trajectories will be something like this. For the different condition, we'll have different circle. So this is also called vortex. So this is stable focus, and this is vortex or circle, or we can say center also, center, right? Now, if zeta is greater than 0, let's look. If zeta is greater than 0, in this case, if zeta is greater than 0, then obviously we may have, this is complex conjugate maybe, but here actually we'll have positive values, right? So in that case, we can say, uh, this, so it may actually diverge, right? Diverging. So this is the condition for zeta is greater than 0. So this, and it is actually, we can say, stable, unstable focus. Stable. This is, we already have done in the last lecture. Now the case is this case. This is very important. So this is actually creates a problem of limit cycle. So here we are not guarantees. It is difficult to conclude where the trajectory start or where to end. So let me say something here. Let me write a note for this particular thing. It's very, very important. There is, before that, question. For zeta greater than 0, for zero, will this is something, or sometimes also we call orbit. These are the orbit, maybe. These are the orbits, how the orbit practically happens. So this kind of things are are required for studying the orbital mechanics. So here, will this orbit go to infinity? So it means for this condition, particular condition, this trajectory will go to infinity. This is the question actually. Now the note is, there is no guarantee, because we derived our remarks, based on the local linearization, or linearized for small perturbation, We can write. So this is what does mean, because if you notice this linearized system we obtained, this is basically for the small perturbation around the equilibrium point, how the system behaves, right? Actually, if you write more practically, if you want to write this expression, we can write this expression. It should be delta x dot, x1 dot, delta x2 dot. These are the part of variables, right? And 0, 1, -1, and zeta, and delta x1, delta x2. This should be the actual equation. This is basically part of system, right? And we are studying how this part of variables is going to behave over time. This is actually we are doing in the state trajectories. So now let me go through the note again. Thus, it is difficult difficult to comment that it will continue to diverge. Maybe after some time, because this conclusion we derive based on the local linearization. Maybe after some time, that may be again converge, right? So that's why it is difficult to comment. Also, if you go away from the singular point or equilibrium point, there is no guarantee the local linearization will valid. That is obvious. Maybe after some time, hence we can write after some time the orbit still incoming to the towards, you can write towards the equilibrium point. So based on this comment, we can come up some kind of phase portrait, something like this. Very, very important. Something like this. It may be maybe for some condition of zeta, we can have the unstable focus, but some other condition, maybe we can have something like this. Maybe it is incoming one. And so it means in between there will be some different orbit which will be stable. So it means we can write here, it's very, very important comment. In between this orbit, there will be some orbit which will be stable in both sides, right? Both sides. So this is how it means we can comment like in between this there can be another orbit which can be something like this, which will be stable in between them. And this is how limit cycle occurs. And this kind of situation we call, if this kind of orbit arises in the system, it is called stable limit cycle. And if for the different, if the orbit is part of, for example, in some of the orbit is part of, and if you have for the due to the perturbation, if you have different kind of circle like this, because this case, particularly this case, it is for at this point, right? But if it is, maybe it's not part of, but if it is part of, it may deviate to another orbit, and this kind of orbit is called, unstable. So this is how the limit cycle occurs in the system. So it is difficult to comment. So in particular for our example, this is the condition. actually keeps the limit cycle in the system. Now we'll have the MATLAB code for this particular example. So let me go through this MATLAB code. If you notice here, we have the equations. We have the two equations here, and this is the dot, and we have used the OD45 to solve these nonlinear equations. And if you notice here, x1, x2, they are oscillating with constant amplitude. Actually, sustained oscillation is there, and throughout the orbit. And if you notice here, this is actually limit cycle, and this is our origin. This origin, and about this is something happening like this. So what you have explained here, something here, same thing is happening here. And this is actually limit cycle for this particular example. And this example, this MATLAB code for this example. But here, if you notice here, we have taken this example, we have taken for a equal to 2. Now, you can try in MATLAB, in your MATLAB window, you can try place. You can take A if A is less than 2 and A if it is greater than 2. So these two conditions you can please try. So maybe you can take A equal to 1 and A equal to 3. So how you can get this kind of response? You're supposed to get, for one case, you're supposed to get this and this. So one condition supposed to you have this, another condition supposed to have this. So in the last lecture, we had many examples. So you can follow the same procedure, how to find the phase portrait, one variable with respect to another variable. So this is x1 is plotted with respect to, x2 is plotted with respect to x1. So this is the same way you can follow to write the MATLAB code for the other examples, what you have done in the last lecture. I hope this will help you out to understand the limit cycle and also to write the MATLAB code for phase portrait, to getting the phase portrait of the second order system. Let's stop it here. We'll continue from the next lecture. In the next lecture, we will come up the Lyapunov part, how we can analyze the system using the Lyapunov function. Thank you.